Vitamin B6, also known as pyridoxal, shows very similar biochemical properties to the other B vitamins. That means that it's used inside of the body's cellular processes to produce energy. Toxicity in the body is very rare because it is able to be excreted by the kidneys if there is any excess, but that also means that deficiency in vitamin B6 is more likely because it has that ability to be excreted by the kidneys, and that may not always be a good thing if you are lacking vitamin B6 in your diet. Now, in terms of deficiency, it often shows pellagra-like symptoms, pellagra being the deficiency of vitamin B3, but there is no name for the deficiency of vitamin B6. Now, in terms of its symptoms, you'll often find cracked lips, cracked nails, and general inflammation of the body are quite common symptoms of vitamin B6 deficiency. Now, in terms of the foods that vitamin B6 is commonly found in to avoid getting such horrible deficiencies, fish and beef liver and organ meats are common sources of vitamin B6. You're also going to have starchy vegetables and fruits, such as things like apples that contain a lot of these complex carbohydrates. Then potatoes are probably the most starchy vegetable out there, so that will contain a lot of vitamin B6. Now, there are 3 different forms of vitamin B6 that can be utilised by the body. Obviously, pyridoxal, this can also actually be known as pyridoxine. Then you're also going to have pyridoxal, which replaces the alcohol group for an aldehyde. And then you're also going to have pyridoxamine, which replaces the aldehyde or alcohol with an amine group. Now, in terms of the base structure, it's got like a pyridine ring and then a couple other chains. And then there's one chain which has this either alcohol, aldehyde, or amine group. Now, all of these can be absorbed inside of the body, and eventually they'll all be converted into pyridoxal. Now, pyridoxal can then be converted into vitamin B6's active form. Pyridoxal plus adenosine triphosphate turns into pyridoxal phosphate, which is the active form, plus ADP. This reaction is catalyzed by pyridoxal kinase. Now, in terms of the specifics about what types of reactions it actually participates in, now transamination reactions are probably the most common use of vitamin B6, and this is where you will replace an amine group, probably on an amino acid, into a carbonyl group, which is a C double bonded to an O. This will turn the amino acid into something known as a keto acid. As well as this, it will participate in some decarboxylation reactions where CO2 is released. This is often still involved with amino acid metabolism and synthesis and stuff like that. Vitamin B6 in general is mostly often involved in amino acid and protein metabolism, and because proteins are macronutrients and able to be broken down into energy, that is why vitamin B6 is a B vitamin, because this is its contribution to ATP and energy inside of the body. Now, pyridoxal phosphate is involved in making some very useful molecules. Niacin, vitamin B3, can be synthesized in the body by tryptophan, which is an essential amino acid, which means you still need it in your diet because the body can't make it itself. Now, only 10% of the total blood niacin content is often coming from the fact that it was metabolized from tryptophan, because tryptophan is often used to make other things such as neurotransmitters as well. But pyridoxal phosphate is utilized in the process of turning tryptophan into niacin, and having vitamin B6 available to still have this nice little reserve of niacin is going to mean that you're less likely to experience some vitamin B3 deficient symptoms. Now, as I said earlier, vitamin B6 has pellagra-like deficiency symptoms, and if vitamin B6 is actually used to make vitamin B3, then if you're deficient in vitamin B6, you're also going to be partially deficient in vitamin B3. So the two sort of deficiencies are actually quite linked together, hence why they will have similar symptoms. Now, in terms of the mechanism of action for vitamin B6's transamination reactions, you're going to have your pyridoxal phosphate, which is going to be enzyme bound to a lysine amino acid inside of the enzyme's active site. Then you're going to have this amino acid. It can be any amino acid. The NH2 group will come along and attack the nitrogen that the lysine is bound to on the pyridoxal phosphate molecule, and that will kick off the lysine, and the lysine will take an NH3 group, and so then you have this amino acid that is bound to the pyridoxal phosphate molecule, and then an OH group, which will probably come from water, because water can often ionically sort of split and dissociate into an H plus ion and an OH minus ion. This OH minus ion will attack a C and cause a C double bond to an N, which is an imine group, it will cause it to break and only turn into a single bond. OH groups are often susceptible to dehydrogenase reactions, where the H will be taken off and then the oxygen will become double bonded to the carbon it was already bound to. And this is exactly what happens in this reaction as well. The H is stolen by another sort of amino acid in the active site, and the molecule is going to dehydrogenate, and because you're adding an extra bond to the carbon, the original single bond now between the carbon and the nitrogen is going to have to break. And so your amino acid goes away, you've ended up with a C double bonded to an O, and the nitrogen has now been transferred to the pyridoxal phosphate molecule. This actually turns into pyridoxamine phosphate, and then that can then be converted back into pyridoxal phosphate for further use inside of the body. So it's a continuous cycle. It's one of those vitamins that once you use it once in a single cellular processes, it can then be used again still, which is good because it means that you don't need a huge amount of it inside of your diet. Now, in terms of the decarboxylation reaction mechanisms that vitamin B6 participates in, if you imagine a molecule of histidine, histidine can be converted into histamine through one of these decarboxylation reactions. This histidine molecule is going to substitute for the enzyme-bound lysine, just like the previous amino acid did in the transamination reaction mechanism. But instead of turning the amino group into a carbonyl group and converting it into a keto acid, the amino acid, the acid part of the amino acid, which is a carboxylic acid, that is essentially a CO2. It's got a C, which will be double bonded to an O, which will then be single bonded to an O minus. And that will be because it's had an H plus R and it's associated with it because it is an acid. That will then break and become CO2, and then you're just left with histamine. Once the histamine then also disassociates from the pyridoxal phosphate molecule, you're left with histamine, which is useful in the body to fight off allergies, but it can cause like inflammation and stuff when you get like bites, and you need antihistamine to sort of stop the inflammation and the pain that comes with it. But it is still a useful chemical that is involved in a lot of your immune system responses. Once these keto acids have exited the enzyme's active site, they're then going to actually be able to participate in things such as the Krebs cycle and be metabolized into intermediates of that, as well as things such as pyruvate, and be involved in the body's energy yielding processes. But none of the energy yielding processes contain any nitrogen, so that is why this process of transamination is so incredibly necessary. With that, I recommend subscribing for more content like this, and have a good day.